Hi, welcome to this Open Security Summit session. So in following up with the sessions we did during the last summit in June, and in preparation for the summit that we organized again the next year in June, also hopefully, well, not this year, but hopefully next year will be on-site and virtual. We now want to organize a series of like monthly sessions where we continue to talk about the topics, we continue to talk about the projects that we've been working on, and I mean basically we continue to evolve the thinking about some of the stuff we do and to collaborate. So today what we have is a session of a project that we're doing at Glasswall around the development of an ICAP proxy solution. But it's a project that in addition to I think technologically being quite interesting, I also feel that we're doing quite a lot of innovation, a lot of good, interesting thinking that we want to share with the community, but also that it's just not just about technology, it's about the processes, the structure, how we're organizing things, and a lot of very interesting innovation that we're actually pushing through. So this is kind of what we want to walk you guys through, and please, please ask questions, please, let's make this an interactive process, because the logic here is not for me to just be presenting. It's more of a discussion, and I'm sure some of the stuff we're doing, is going to be thought-provoking. So hopefully you guys are going to have some good feedback on it. So let me just share my desktop, and then we can start. Okay. So you should be able to see my desktop.
Yes.
And so let me just, first of all, I'm just going to give you a very quick overview of where we're going. And then, just to also give an idea where we're going to arrive, we're going to basically arrive at, dynamic threat models, about, sort of kind of ways of thinking on how to apply security into the threat model, and kind of my evolution again, and the thinking of how we actually make some of these things scale. So the first key part here is that we were basically, Glasswall, in essence, has a product that we can make file safe, right? So that's kind of what we do. It's actually a really cool product. It's a graph. We take a file, we build a graph of a file, and then we rewrite using known good. So the key thing here is what we're trying to do is, the early thinking was, okay, the users have to make secure decisions, right? So the user wants to go to SharePoint, he wants to download it, but the question is, we push security to the user. And this is something that I always have a bit of a problem with the industry, which is we make the users responsible for the safety of the files that they click on, right? We make the users, almost have this cognitive load of having to make a risk-based decision, when the reality is users want to open a file, they need it as part of their day job. We thought, they learned, right, that, opening in files is how you get stuff done, right? So, and it's very hard to do that, right? So one of the topics we start to zone in is this idea of patient zero, right? So I really don't like the 0-day stuff, like that's a very overhype used. I really like this idea of what we're trying to do in this case is actually reduce that first infection, right? Especially because a lot of companies, that tends to be very hard to contain, but the idea is that let's reduce the maximum amount of this, right? So the logic here is that, a lot of the times, one of the crude solutions, they look for known bad, right? So if the users, basically open a file, that's maybe you can intercept the file, and it sends to kind of malware detectors, antivirus, detonation chambers, and in that case, if you don't see known bad, you actually send the file to the user. What Glasswall tries to do is actually, instead of looking for known bad, it looks for known good, right? So Glasswall basically rebuilds a file and creates a new visual identical. So, and I'll go into a bit more detail in how it works, but also how the open source part of everything fits. And by the way, everything I'm going to show today, which is part of the reason why I can show you, is open source, except like that final little bit, or that core bit, which is the bit where you create the file in the Glasswall engine. But the whole infrastructure, the whole thing we're doing, especially to make it scale, it's it's all open source, right? Which I think is actually quite cool. So this is fundamentally how the engine works. We have three. We basically think about having three layers. There's the visual content, the functional, and the file structure layer. And basically, the idea here is that we want to leave the visual content intact, but we basically want to apply a policy onto the functional layer for macros, JavaScript, etc. But also we rewrite the file structure, which is quite cool, because it means that we actually make the files safe against buffer overflows and all sorts of other problems that could exist in the file itself, right? And in this case, if you integrate it with F5 or a proxy, you got this nice transparent user, workflow, and then the users don't have to worry about this, right? So we try to create some marketing materials around it, and here's what's kind of the story that we come with it. So we have users working in a secure building, an internal network. COVID happens, all users have to go home. Then, in this case, our client actually needed to put SharePoint in front of it. SharePoint is part of Office, right? But then now that COVID is under control and the users are coming back to the office, the question is, what do you do with all those files that were created in SharePoint, right? And the challenge is, because there's a large number of files, this needs to happen in a transparent and user-friendly way with minimal existing overhead, right, to the security teams. So what we want is to make sure that the files can be brought into the safe network, but a number of files could be malicious, and some of them can even maybe design it once they go back into the internal system. So what we need is a solution to get those files internally, and we break it into three parts, which is the proxy with the ICAP protocol. ICAP is the Internet Content Adaptation Protocol. It basically means that it's a way to intercept a file in the proxy. It's like a language to send files around or content around. There's the antivirus bit, which is your known for bad, look for known bad. And then there is the Glasswall proxy server, which basically is the one that actually intercepts so basically rebuilds into known good. So that's the kind of solution. So every one of these companies provides an ICAP protocol, which is really cool. So that means that it's actually a great place to put security. And this is something that for me was also, it's something that I thought about a lot in the past. And I've always dabbed with, firewalls and web application firewalls and being able to be in the middle of the traffic. And I feel that it's a great place for security to be, right? Because you get maximum visibility, and I feel that you can apply a lot of things. So, at the moment, we focus on rebuilding known good for files, but you can do the same thing for web requests. You can do the same thing for JavaScript. You can do the same thing for links. You could do the same thing for all sorts of policies, all sorts of things that you could do if you happen to be in the middle of the traffic. In fact, even the latest zero logon, if you're able to be in the middle with, for example, the Kerberos handshake, then you could actually prevent those exploits from occurring, right? So it has a very real worldiness kind of factor, because it doesn't require a change to the end solution, which is kind of a key requirement. It's very hard to patch the other side. It's very hard to drive change. And as a security, we know the logic here is that if you can do your activities in a proxy in between, you have a lot of power, and it's very easy to plug in and out. So again, it's much easier to deploy, etc. So the antivirus kind of it's a valid solution. If you can tell that the file is bad, of course, don't let it through. The problem is that they only know when something is bad. They don't know when something is potentially bad or or could have other issues. So that's why the kind of this industry, which Glasswall is part of it, but there's other there's other vendors like OpSWAT, Deep Secure, there's a whole bunch of them out there, right? And basically, it's about this idea of content disarm and reconstruction technology, right? And basically, that builds files into a known and safe good, right? And this is kind of the workflow. User clicks on a file, downloads, I said F5, sends it to one of the engines, and then sends it to Glasswall, and now the user doesn't have to worry about the file, which is really cool, right? And and we support file types, Office, images, just about the majority of the files that will have weaponized payloads and are dangerous. So and on this one, he's also have to work for a massive website, right? 3 million users, 800,000 active users, etc. Right? So you can see it's a massive project, which you'll see why we developed this architecture. So now this is the cool stuff, right? So this is now the architecture that we built for this, right? And remember, please feel free to ask questions, right? Or actually, you could also paste them in a chat. And Daviana, if you keep an eye, or Georgine, if you guys keep an eye on the chat, let me know if there's any questions there that you want me to address. So this is kind of fundamental the process, right? You have ICAP device, the ICAP server into, this is what gets called, and then the resource, is basically the actual bit that is Glasswall specific, and then this actually will call what we call the adaptation system. We call it because it's the ICAP, so internet content adaptation. So that's kind of where the name came from. We have this concept of non-compliant file server, and then there's the all the transactions, all the monitoring, and the policies, right? And there's a number of really cool design decisions that we made here, and I actually feel that, and I'm very proud of how we arrive at some of these decisions, because a lot of those decisions was actually driven by security. We actually have already great case studies here where we basically already use security and threat modeling to drive design decisions that made the solution much better, much more resilient, much more robust, but fundamentally better, right? And I feel that security has to have that high bar, right? If the way I look at it is that if security wants to be taken seriously, and if you want security to have a seat at the table, security has to add value, right? It can't just be an insurance or reducing risk a little bit, right? So in this project we have some really cool examples, and I'll walk you through some of them where security really added value to this project. And then the second part, and this is actually a good example, right? So one of the key requirements that we had for this was to make it almost cloud independent. So we embracing multi-cloud almost from the get-go, and it's very interesting, right? There is, I really have to say that there is such a vortex of attraction to be locked into a cloud, right? Especially when designing systems, and I would actually argue that developing something that is multi-cloud from the start has, again, massive design advantages, right? And also from a security point of view, from a testing point of view, from a deployment point of view, makes a massive difference. So what you see here is that we decide to build all of these in Kubernetes, because Kubernetes is the sort of the current standardized way now of deploying containers. And then when we arrive at this mode where literally we can run this anywhere that you got to compute, right? So as long as you can give it compute to a Kubernetes cluster, i.e. by Azure, EC2, ECS, or just OVAs or VMware, then you can run the thing. And then the only couple little things we have is actually, some secrets to set up, but then the file storage just for logging, right? And then, there's some load balancer fundamentally for initial load, which some of the proxies can do, but actually to try to minimize some of the work that is done by the proxy. But even the load balancers with a more evolved proxy setup wouldn't be needed. But the power here is that we now have a solution that can easily be deployed from a very small environment to a very large environment. And what this means, it means that if you look at it from a testing point of view, we're making the testing and the deployment and the testing of the application a first-class citizen, because everything is designed to start from scratch. So the whole system is designed to start from zero, i.e. all we have is a couple of Docker images and some Helm charts and some Terraform scripts, all the way to spin up the whole thing from the ground up, which is really cool, right? This is sort of the data flow architecture. Very simply, the user makes a request to SharePoint to get the file back. Then, he hits the load balancer, and the load balancer, one of the jobs is to make sure that there's minimal configuration on the ICAP, in this case, client. Then he hits the ICAP server. This is already load balance, and then there's already a queuing system. So this is pretty cool, because in this ICAP server component is going to have to keep states, and it's going to have to keep an open connection, but everything else from it is event driven. So what happens is you put an event, you put the file that you got into the original store, then you send the file down to a queue. So I put a message in the queue, which is then picked up by the job who does this thing, and then it goes, sends the results into the queue, and then puts on the file system, which is picked up. And by the way, in terms of design, this is, in principle, this might be mini IO, this might be RabbitMQ, but we're exploring other options, but they seem to be doing a good job at the moment. And but the point is that this is all a Kubernetes cluster, right? And then we have another cluster, which you'll see in a second, that puts the actual admin management console of this. So so his was a really cool architecture that we built, because the way you need to think about this now is that the way we scale, and this application now is designed to not crash and be able to scale as much as you want to pay, right? And that's very important. So the logic here is that we want a solution that even if we've been hit massively by a stupid amount of traffic, the application should still be able to process files. The application should still be able to process files at a decent level, because as long as there's enough resources in the cloud or in the environment that you are, it should just be a case of provisioning nodes and provisioning even more clusters. So that we designed this from the ground up to be multi-region. So the idea is that when you look at the ICAP proxy, the ICAP proxy basically, is the one that receives the request from the client, and the ICAP proxy is given, for example, in this case, 5, let's say, IPs, which is basically the load balancers, right? So, and then the load balancers would already load balance the traffic between 2 clusters on each region, and we can add more, but we're kind of going to at the moment, and then each cluster looks like this, which I'll go into more details now, right? In fact, this is actually not the latest one, but because the concepts are the same. So basically, the power of this is suddenly you have a lot of scalability, because remember that in Kubernetes, each cluster has nodes. The nodes is a VM, and inside each VM you have the pods, which actually are the Docker virtual machines, right, or the Docker container image running. So what this means, it means that we have a huge amount of scalability, because the clusters can auto scale according to a set of policy. You can provision hundreds or thousands of machines to run inside each of these clusters, right? And then we load balance it so that you get a huge amount of scale, right? And inside the cluster, what you've got is this architecture, kind of as I mentioned before, where the request hits the ICAP server, the ICAP server puts the file, service puts the file into the original store and the queue. It gets picked up by a service that is listening to the queue, and it starts a pod. Now, this is a very critical piece of the solution. We made the key decision to run one file, one pod. Now, although this has some performance considerations in the short term, actually overall it has a huge amount of advantages, right? And actually it has a huge amount of performance advantages, again, when you think with volume. When you start thinking about 10,000, 20,000, 30,000 files being processed at the same time, up to 100,000 or 200,000, this scalability becomes super powerful, because the pods becomes this entity that is actually going to be responsible for processing the file. And then once it's done, once you have a save file, it actually moves into the outcome queue, puts a message here, and then that's sent back to the client. And here's one of the key decisions that we also made, was this idea that the only state in the whole thing is the transaction logs. Right? So, put it this way, the only state that persists after a little bit, right? During the file processing, yes, there's a bit of state where the file exists for a little bit on the original store. There's a message in the queue, and the file will be in one pod, and eventually will be on, if the file can be rebuilt, it goes, it actually exists also over here. And we have this also massive key concept from a security point of view, that any file that we don't process, we're going to send it to what we call a non-compliant file service. And you'll see in a variation of the architecture that we actually have a version of this where we actually provide a cluster for this part. But this also means that, in terms of where the content exists and what's the worst case scenario, we're looking at a situation where the most dangerous part happens inside the pod, because that's the only place where the files is actually parsed, is actually processed. Although the Glasswall engine never executes it, that's the place that it's the most dangerous, because we literally are processing potential malicious files. We are handling files that some of them will be malicious, will be known malicious files. Any questions?
Dinis, we have a couple of questions in the chat.
Oh, all right.
So the first one is from Felipe. If the idea of this is real time.
Yes, absolutely, right. Oh yeah. Totally real time, right? So yeah. That's the point, right? The point of this is, in fact, I can actually show you the, actually maybe I should have started like that, right? So here's here's just an example of this working in action, where what you see here is basically so if you look here. what you have is this is, you access the file. Okay, so that's the punchline, right? So the punchline here is that you've got two versions of the proxy, one where you go directly, one where you go through Glasswall with F5 integrated. And the logic would be that, if you go directly to the file, you could see, it opens normally. But if you open the same file, using the second part, which is basically using the the proxy, you get to see that actually, we put a little thing there says Glasswall approved. That means that we have processed the file, right? But in this case, a cool example is that if you basically download, for example, this file that has a macro, and these days, even on, I go back to the zero log on because it's just a crazy exploit, but this is kind of one of the problems, right? So you download a Word, it has some macros, the users will enable these things because, some of them, they actually need this for business context, and now you got remote code execution, right? Bang, right? So the logic here is that if you download the same file, and there's the macro, right? If you now download the same file using the Glasswall engine, then what you've got is basically, a workflow where you download it, from a user point of view, it's still the same thing. You can see the McAfee will have a go downloading this. And then, you actually get a situation where now the same content, the same structure, but there's no macros, there's nothing there, right? Because we actually cleaned up the files, right? So, that's quite powerful. And there's actually a really interesting thing here where, you can actually, download, for example, a file that we know has been infected, where, and this is something which it's a bit, you probably don't, in some real world, you have to be careful if you do this, but in this case, the user is actually able to download a file that's been recognized infected, and even, there's a secure alert, you still allow the file to be downloaded, which sometimes takes the real world scenario, because the users, sometimes they need files, and if you don't allow this, if you don't allow the user to get the file, you actually create a massive business blocker, right? Because especially with lots of files, it can become a massive problem. So in this case, you can still download it, accept the risk, but in this case, again, when this file is now infected, right? But if you do the same thing through the Glasswall engine, so this was the directly, if you do the same thing through the Glasswall engine, you actually can download it, and actually you could see that by now the scan won't pick it up because it actually been processed by the Glasswall engine. So we happened before the AV, and now you can actually double click on it and you can open it. And this is an example of some of the malware where we've seen where you can basically see that it's a bit of a social engineering tool where say, oh, document is protected, you have to open it, enable editing, enable content, and then tell the user, then you see the stuff. Of course, this is how you actually deploy, and there's actually ransomware that's been deployed like this. So yeah, so Felipe, absolutely, this thing has to work in real time. And by the way, he's sort of the update architecture where we actually added a cluster for the non-compliant file server, and we actually added Prometheus for logging. Cool.
Dinis, he confirms that he was referring more to the queue process, and also he would like to know more about the scaling of this solution and the limits.
So yeah, so the queues, so the logic is it's event driven, right? So if you look at the workflow is that, in fact, I can actually show you the design document in more detail. Basically, so inside that that bit, which is what you see here, right? I'll show you so this is what happens, right? So basically, the ICAP server picks it up. So the workflow is this one here. This is what the endpoint looks like. So you call that guy. That's what the ICAP server calls. This actually, will start saves the file locally that extracted from the ICAP, and he's going to start a new process that puts it on the original store and puts a message in the queue. So, and the message in the queue is then sent to the Glasswall engine to do the workflow. So the logic here is that basically the process now is listening to the queue. So so this process here, the adaptation service, is listening to the queue and is starting the request processing pod, right? So and this happens very quickly, right? So the logic would be, the point is to run this almost sub-second or maximum a second, if the file is not very complex. And the Glasswall engine will process a file in about 1 or 2 seconds, right? Depends on the complexity of the file, but basically processes files quite quickly. So that was the first part. What was the second part of the question? So it was the queue, and then
the scaling and the limits.
Yeah, so the scaling and limits are interesting, right? Because we actually trying to actively find the limits, right, of this thing, right? So the logic of this is to actually, like we said here, right? So we basically we're designing kind of each of the clusters to handle 5 to 10,000 pods, i.e. Concurrent files going in parallel, right? So the logic here is that we basically initially proposing 5 regions. You can have more, and we basically proposing running 10 clusters. So our current projection is that we should handle 100,000 requests happening at the same time, which when you look at it, it's a hell of a traffic, right? It's a huge amount of traffic that is being sent to the proxy service, right? To this, and the theory of this, which we're kind of proving, is that the system should continue to scale even if there is insane amount of traffic, right? Because it's just a question of keep starting more nodes and keep adding more capability to the solution. Did it answer your yeah, denial of wallet? Yes. That's correct, but remember that you kind of have that problem with a lot of websites, right? The question here is that we want to make sure that we scale according to the sites, and our basically the logic is that for certain type of attackers, they will struggle to create a huge amount of traffic that mimics normal users, right? So the logic is the higher the amount of traffic a user will send, the easier will be to block it, the easier will be to stop it, because there will be a pattern that you can stop it in a way at proxy level, right? Because the proxies, remember that these proxies have security features in itself. Cool.
I'm having another question.
Yeah.
Is it mainly for having storage behind it, or also for applications? Because when I have an application, it might be base 64 decoded or something else.
Yeah.
So I'm wondering if that solution in general is able to handle it.
You mean normal content, not files?
Yeah, I mean when I have an application behind it.
Yeah.
Then developers might think to decode a file via JSON and upload it because of, I never understood the reason, but that's what they do.
Yeah, so you're saying is that what if the application sends files through base 64 or encodes, or there's some kind of weird stuff in it, right?
Correct.
Yeah, so the interesting part of this solution, right? And part of our go-to-market here is also to build this focus on reverse proxy. And what it means that, when you look at proxies, there's 2 ways that this can be developed, right? There's the global proxy that you can have, which is a proxy that intercepts all traffic. And you also have the reverse proxy that basically intercepts one file, right? So basically it stands, between one, let's say, a normal website and one site, right? And basically the logic here is to actually, sorry, just give me find where's my thing. Here we go. So one of the logics that we have is that we want to make this transparent to the user, and we actually want this to look, to be able to intercept the content in the middle, right? So I was trying to find a presentation, but I don't think I can find it here. But the concept here is that, let me put on the reverse proxy. So when you are reverse proxying, i.e. when you are in between the user and the end result, you actually have an interesting opportunity, because you have an opportunity to actually change content, right? And so I would say that one of the powers of the solution, although we initially are going to focus very heavily on on just the pure files, i.e. the files that are normal files being recognized, is we actually building a variation of it where we also will be modifying some of the content, i.e. the HTML, in specific cases to make it work for specific websites. So the reality is that this is something that you have to do if you want to make this work for particular sites. So my point is that for every site, there's and this is sort of why it's powerful to have this sort of, again, these what we call non-compliance file service, because we will be pushing to the non-compliance file service any file that the engine doesn't process. So the logic would be that if there's HTML or like you talk about maybe files encoded in a particular way, we actually have the opportunity to add site-specific logic that will add some changes to the sites, or will, let's say in that case, decode the base 64 into a proper file, and then let the processing continue. And I think this is super powerful, because what it means that you want a model where per website you could choose what, even on HTML, what changes you want to do both on the way in to the final server or on the way down to the final server. So I think in the example that you talk about, I would say that if a particular website does those kind of things, then the logic would be to make a couple of changes into what we call non-compliant file service here, which basically gets the raw file and then run it, almost feed it back to the original store and let that continue normally. Does that make sense?
Yes, I understand.
The power, in a way, of what's interesting about this solution is that we are reducing a lot of the requirement of doing those changes at scale, because those little tweaks, those little unique changes don't have to happen for every file, right? Don't have to happen for everything, because it's only let's say in this case, the files that the engine doesn't process, that it doesn't send, that it hits there. And this version doesn't contain caching. We've done, some variations of this, which actually, this is where security gets interesting, because, it has some security implications. But this version doesn't contain, for example, the caching of results that you could also do to optimize a lot of these things. Cool, right? Any other questions? All right, so what's interesting now is that, and this is where the threat modeling becomes interesting, right? So we then took this and we, and actually one of the things we created, which was really cool, was we also created this concept of, and actually the other one is we also created this really good testing solution. So what's interesting about this problem is that you can actually see here that in order to test the solution, we actually need to almost create the same thing just for load testing this, right? So we actually are using the same structure, using Kubernetes and creating test engines where we can literally not just hit the proxy directly or the ICAP endpoint, but also go to the proxy and confirm it, where we basically building a scalable testing infrastructure that allows us to generate tests that can, make 4 million file requests, send, 10, 20, 30, 100,000 requests in parallel, right, or up to that kind of amount, and basically scale at that level, because it's quite, in fact, that's as much of a challenge initially as building the initial cluster. And again, we're using the same thing. So we're using the exact same technology for the final product, which is the ICAP solution, and the testing APIs that we're using to build this thing, right? To test this. And in this case, for example, we want to confirm that if we hit the site directly, if we hit the ICAP endpoint directly, if we hit to the proxy. So these deltas are important, right? It's important for them to understand, does the proxy introduce any latency? Does the ICAP endpoint introduce any latency? And even on that architecture, does the, where are we? Does these parts here, does the processing part, the queues, like I think Flip was saying, like what's the heaviness of this? So we actually have test suites that are hit directly the request pod, test suites that start with the original store and the adaptation queues, test suites that hit the ICAP server, and then test suites that are going to hit, actually, we want to probably the load balancer, but also the final proxy. So it's important then to compare the deltas for each of these and understand where are the bottlenecks and where are the kind of the key concepts that, from a performance point of view, right, where you're going to have problems. And this also has a lot of advantages because it forces a lot of good discipline, forces a lot of clean patterns in our system. So for example, the transaction event store, we actually decided then to actually put an event that gets triggered, who then is subscribed, who then writes it, in this case, to either S3 or blob storage or a local file system, if this is on VMware or something like that. But again, that triggers the scalability of the system. And again, from a scalability, is super important, and the fact that each of these containers or these clusters can be completely destroyed. And if anything, the only thing you might lose is some file processing that are currently happening. But the logic would be that we should never lose any data. We should never lose any kind of service, especially because as this gets degraded, right, we can eventually stop a whole cluster and the other one will pick it up. One of the cool things that we created was also these design principles, right, which I walk you through it, right? So the design principles, it's almost like these patterns that we basically address, and this is fundamentally what this does is this helps to define what is a vulnerability, right? So almost like this allows to say, if you find something that breaks the security posture of these principles, then that's a problem. And if not, this is the model. So in this case, the logic here is that we want to rebuild it to known goods, right? And this is a massive one, right? So we're basically saying that no further action or decisions are implemented on the security of the file, right? So that we push this. But this is the massive one. All logs from the data analysis contain no confidential data. But this, of course, there's a massive challenge here because we want to have a good set of logs, we want to have a good set of data, we understand what's happening in the files. So there's a lot of work that's been done to make sure that, for example, even something as the file name never gets propagated, right? And the file name, for example, can be massively sensitive. So we pay attention to that. And this is the other pattern. Every rebuild process performs its own container, right? And then so basically the container is provisioned and then we destroy it. The problem is, if you don't do this, it means that the ICAP server is the one that ends up doing that. So let's say, maybe the original design was the ICAP service was responsible for that, but that means that if that guy pops, then on the next request, suddenly you could have a file that now gets infected or gets different behavior caused by the previous file. This is why lambdas and the current Azure functions don't work for this, in addition to the performance limitations and etc., because the lambda functions don't do this. The lambda functions don't start a new process. Literally, they will run all of this in one process, which basically means that if there's a problem in one of the executions, even memory leaks or stuff that got left behind, it will affect the next execution. So that was a key pattern, right? And again, the Kubernetes clusters are stateless and can be destroyed and recreated on demand. I'm finding more and more that this is probably one of the biggest issues that people tend to have with Kubernetes clusters. And the reasons why usually people go, ooh, make sure, are you sure you want to go for Kubernetes, or make sure, there's monsters, right, in that environment, is because I think a lot of teams, they don't view the cluster as the application. They almost view the cluster as something they set up a couple of times and then that's it, right? Where what our logic here is that our clusters should be created, if you want, every day, every hour, right? We should, creating a cluster is simply a process of deploying a couple of, Helm charts with Terraform scripts, and they should pop it up, and then just a case of adding nodes to it. And that has huge advantages from deployment, for security, for testing, but also for scalability, right? And resilience, because we can now deploy clusters around the world, right? Which is kind of the idea. This is the other massive concept. Confidential files never leave the Kubernetes cluster, and they're only located inside the ICAP server, protocol, and temporary storage, right? And that, again, that we're limiting the places where the data is actually exists, and there's actually a plan to even start to encrypt the files even inside these locations. So we even reduce maximum the amount of time that a file content is available almost in clear text. And again, least privilege applied to the whole thing. Now, what's interesting now is this idea of doing the thread model. So here's a thread model that was created, and this thread model, is actually pretty good, right? So you could see that it follows the web server that hits the request, the web proxy. There's the ICAP, there's the original store that gets put, there's the queue, there's the adaptation server. There's some stuff that never gets identified because if the request processing pod needs to be started on demand, that means that the adaptation server has to be able to talk to the Kubernetes API, which actually means that, for example, this service is massively dangerous, right? This would be one of the high, it's almost like, in a way, this server is not root, but it runs with a very high privilege already capability, because it can actually call the Kubernetes API and can actually start new pods, right? And then there's the pod that does the work, there's a non-compliant file service, there's the configuration store, and then the transaction queues. So what you can see here is one of the good news of this mode is that we limit the most dangerous part of the whole engine is literally, or the whole solution is inside this box here, which is the request processing pod, which is the one that actually will take the Glasswall engine and process the file, right? And of course, the point of the Glasswall engine is to do it safely. But if there's any problems or it crashes or any kind of issues with that workflow, this is the one that we want to make sure that gets destroyed very quickly, right? And only lasts for a small amount of time, which actually creates lots of challenges from a logging point of view, because it means that if there is some problem with the pod, by the time you get an alert, the pod is long gone, right? And so there's also sorts of interesting questions, right, of how we handle that, how that gets processed, what gets persisted, etc., right? But it's a massive design pattern that, if you think about it, if we didn't do this, if this pod was long living, like, then this untrusted file processing would probably be massive, right? And now one of the things that we have to be careful in Kubernetes is who can talk to who, right? So one of the challenges that we have, and this is part of the problem now I want to tackle next, is that technically you should be able to now to see who can talk to who, right? And if you don't apply, strict, for example, isolation between the pods, it means that although technically, right, the request queue, or let's say the original store, can only be accessed by this guy, what's preventing, this one to access there? What's preventing other pods to accessing that information or putting more stuff into the queue, etc., right? So, and also, or hitting the ICAP resource directly, or hitting the transaction event service directly. So, there's also all sorts of things that we want to do to limit the maximum, so that each pod or each service can only talk to themselves. So sorry, to the ones that they need, and that's that's where it becomes a gigantic graph. Now the challenge, and this is actually this is done with the thread modeling tool, right? Which is one of the tools that you can use to create. My problem with this, which what I want to walk you next, is that this is now already starts to be a bit out of date, but also in security, I feel that one of the key principles is for security to be the single source of truth. So what we know is we want a situation where security should be the one maintaining not just this, which is basically a kind of a more threat view of the system, but security should be maintaining this architecture, right? Should be maintaining this flow. And that's kind of what I talked today about on the map camp, because my big paradigm shift was, how do you move from thread models to worldly maps, right? And here's the thing, right? So this is the proxy. So we covered this already, etc. So if you look at, and this was the original version of the thread model, so you can see it's a bit simpler, but it has the key components. And then I'm really proud of this. This was one of the things we did. So you guys know me, that I'm a big fan of Jira. So one of the things that the team already did was, you already converted a lot of the risks and the threats. So basically took these tables here of assets, vulnerabilities, risks, etc., and he basically mapped it to Jira tickets. So what you see here is basically, the thread model that maps to, has a bunch of vulnerabilities, who affects the system, who are they mitigating by this, who have, a particular, control associated, or a project that is going to address it, right? So this is, and by the way, every dot that you see here is a Jira ticket, and this is actually using the open source OWASP security bot project, which is super powerful. So this actually was created from Slack with data in Jira in Elasticsearch on a serverless function. So you can see that we basically have the thread model. The problem is that in a way, this thread model, which is the second version, is actually a work of art, right? So I kind of wrote this article ages ago. It's actually on my book too, and I kind of go and say why, stuff in Visio or Draw.io and all those things really sucks, right? Because, they take a lot of time. It's an person interpretation. They're not created from dynamic data. They're pixel based. They're locked to design convention. It's very easy to mix abstraction layers. They store in binary XML. They mix code and data. They're very hard to update, not an accurate representation, etc. And this is, it's happening when you look at this and you start asking people to make changes, and the team that's supposed to maintain this becomes very resistant to changes, right? And almost they start arguing why they don't want to change, and you end up with almost not an ideal situation, because you end up with sometimes a design that is too detailed for some of the use cases and doesn't have enough detail for the use cases, right? Where the reality is that we need to have as much detail as possible into this, but then be able to abstract out and actually be able to have a visibility on the top. So what we want initially, and this is multiple stages, we want to take the thread model and make it plan to ML. So this is a version of that diagram. So this is a version of this, or actually of this, but also of that architecture there, right, of this part here, but it's now created programmatically, right? So what you can see here is that I'm actually using plan to ML, so where I can say here's my systems, here's my ICAP servers, and then I can start to say, so these are the IDs, so you can see original store, that's the text. So then I can say, oh, okay, cool, my ICAP server talks to the original store, the ICAP server talks to rebuild store, so you can start to see the flows of data here, right? So that suddenly becomes a lot more scalable, because we can start to zoom in and zoom out according to what we want, but also we can now programmatically create this. In fact, those diagrams I was showing you that we create from Jira, they actually are created from plan to ML, where we take the data in Elasticsearch or JSON files, and then we create nodes and edges, who then creates a plan to ML file, who then gets processed. So this version was created by hand, but the idea would be that this will be this will be automatically generated from JSON files, or even actually from the source code, or from configuration files, ideally from Terraform scripts and Elm charts and etc. So now here's a different view, right, of this. So this view is basically a sequence view where what you now see is that it's almost like this calls that, does this, puts in there, etc. Right? So the challenge here, in a way, is that and you can see that it's quite nicely done. If I want to change, I can add one of these, and I think this is using plan to ML, so this is a little bit probably too complex for my taste, but it's already text driven, right? Which is really cool. It's also version control, right? Because the nice thing of this is that once I understand, I know how to read this or this on the left, the next time a version comes along, I can just see what changed. I can actually use Git as a way to diff graphs and diagrams, right? Which is super powerful, versus somebody shows me a new version of a diagram and you go, I show you this one and you go, ooh, okay, what changed, right? And that becomes quite problematic, because sometimes the changes could be little changes, but can have dramatic security implications, right, of what's going on, right? So now the problem is, is thread modeling a map, right? So this is quite interesting, right? So if you look at Simon Warren's definition of a map, maps have to have visual, have to have context, the position has to matter, anchor, there needs to be movement, and then components, right? So if you think about this, almost is a map, but it's not completely a map, right? Because yes, it's visual, there's a level of context, but position doesn't matter, right? If I move this box over here, if I move that box over there, if I change the structure, that doesn't matter. The anchor just about happens at the top, although it's not well defined. In this case, the anchor is actually on the left here, but you kind of want to be more consistent. There's little movement, again, as things move, what's going to happen, what's the evolution, right? So again, if although position mattered, what happens between one position and the other, right? And then the components, which these match. So let's make position matter. So if I took that initial diagram, this one here, and put it like this, now position matter, because there's level 1, level 2, level 3, level 4, right? So now you got the situation where it actually is there's a difference between level 1, level 2. Well, I haven't defined what level 1, level 2, but that's now a better game to play, right? Because now, once we define what that means, it means that we basically moved from a place where position didn't matter to position matter. So now, if SharePoint is level 1 versus level 3, that has implications, right? So let's look at what that means, because when I look at this solution here, what do I build? What do I buy? What do I outsource? What do I basically, choose when I'm developing this product and this solution? What are the stuff that we're going to do in-house? What are the stuff that we're going to get? So, is it that one? Is it this one? Is it that one? There's a funny slide from Simon that he changes this to Elvish, right? Or Klingon, right? And then say, which one would you do, right? And the reality is that if you don't have context, then you don't know if it's correct. You almost don't have a good way to challenge the teams to say, architecture, are we doing the right thing? Now, if I change this to a worldly map, and the worldly map fundamentally is Genesis, custom build, product, and commodity, there's that evolution of something from, barely exists. I have a first version that works, I have a product and I have a commodity, and, usually if that looks is at the bottom, but, I just put that at the top for Plan2ML. Now you could see that, we got the SharePoint, the event store, and the user. There's just commodities, right? Then we got the products that we're getting, and then we got the stuff that we're developing. And of course, our job here is to move this ICAP server to a product. We want to move these guys to the right, but and this is where security is super powerful, because this also means that now, from a point of view of scalability, right? It means that when you do security reviews, for example, you want to make sure that you are co-reviewing and you have a lot of security here, right? So this area here is where you want to make sure that your, almost software development lifecycle, your secure development lifecycle is super strong, because this is where most changes will occur. Now if you look at this other part here, I would argue that this structure, right, should change very little. Right, this change structure here, you shouldn't have, new changes to do this. And in fact, what also it means that not only you want to do code reviews here, and you might actually have situations where you might not be able to review everything that happens inside here, which is a different story because of just the pace of development. You actually want to make sure that anything that changes on here, again, gets reviewed, right? But the logic would be that you don't want to see a lot of activity here, because this should be something that you just buy off the shelf. So in this case, for example, for the adaptation request queue, this guy here, we're using RabbitMQ. So, we don't want to be developing a new queue. We don't want to be developing a new queuing process, but it's very easy to start doing those things, right? It's very easy even to be locked into a particular platform, right? So the logic here is that we want to make sure that, even our Kubernetes environment, we actually don't have a lot of movement in the areas here of the product, because most of the activity should be on custom build. So one of the things actually I mentioned the security team is that they need to raise an alarm bell if they see a lot of development happening, for example, in the bits that we map the product, for example. Any questions, actually? All right. Thanks, Felipe. So yeah, and here's one of the, I really like this next graph, because what it is also the so the logic here is to now say, okay, let's map confidential data, right? So now where does confidential data exist? And in this case, what we now defined was we actually said that this is all the places that confidential data will actually exist. And there's an interesting overlay between this one and that one, right? Because if I map the confidential data with here, you now start to see that, for example, some of these guys will have confidential data, right? Which is important. But now you can see that we're also saying that there's some logging data, and then maybe there's public or static site or open source content that, but here's a very big line. We're basically saying that every event, every submission, everything that happens on the event store actually doesn't have any confidential information, which is super powerful. And what that means, if I actually draw on this map here, what we're basically saying, and on the architecture, if I go back to the architecture. What we basically said from our design point of view, which although in the other map you don't get everything, the logic that we have is that this is the places where actually confidential data potentially will exist, right? But this is very important because you can see that, you know, these are actually and there and there. Well, and of course there and there, right? So the logic would be that these places that are highlighted are the only places where you should see. In fact, this is even wrong because you know, that bit there is actually simpler than that. Is actually the ICAP service. So is the ICAP service, and then oops, sorry, and then there is the original store, and there's actually the rebuild store. The queues should not have any confidential data, right? But you can see that what we're doing here is we're just reducing the attack surface, right? So in this case, we're reducing the moving parts that actually have access to the files. And that's a very important design pattern that you have here, which you could basically clarify with, you know, with the architecture, right? That we actually are talking. So the final design that I want to show you is basically the looking at, yeah. So that's the sorry. This is the data, the confidential data, right? Which we'll map here. And then this is a really great worldly map that I really like, which is you go to each of these items, right? And you ask a question, how fast can you patch this? I.e., you know, even if you say, okay, by the way, this is not 100% correct, right? Because I just want some data to show here, right? So this is now not a good representation of our system. So, but the question would be, when you look at the components that you're working on, even if there's a big vulnerability, right, and there's a big requirement to patch something, how fast can you physically push a fix, right? And this gets quite interesting because you could see in this case SharePoint and proxy. Maybe SharePoint could be a bit faster, depends, right? If you know, if it's really a massive vulnerability. But again, remember that, you know, it's a massive product, so Microsoft will take a bit of time. The proxies, you know, some of these are hardware based. You know, that might take some time to push fixes. You know, this is now the ones we're developing, but now this now assumes that we can deploy very quickly, right? This is where having solutions that are Kubernetes based, solutions that we can just literally push a fix and then deploy a new Kubernetes cluster and rebuild everything from scratch allows us to have this architecture. Without the architecture, this would be days, even if there was a massive, you know, push. So what you now have is an understanding of what is the risk profile of your application. So you can see that some of the stuff takes weeks, some of the things might take days, some of the other thing takes weeks, stuff you don't control. And this, for example, would be an example of, let's say, we don't have the source code. We actually don't know how to build that. So that means that, you know, we can, even if you wanted to fix it, we can't fix it, right? And this is super powerful because if you look at this now, you get to see that rebuild store now is one of the highest risk elements that you have. This is now crazy dangerous, but you'll be amazed how often this occurs, right? And that's the key thing, right? The key part is now to understand where do you actually make decisions, and more importantly, what, you know, should be your focus from a fixing point of view, right? Or even security efforts. And what I found, and this is quite an interesting situation, I found that a lot of teams, security teams, will spend a lot of time fixing and doing things here on these projects. And the reason why is because these projects usually will have a good team. They have, you know, people know, you know, where they are. They have security champions. There's a lot of activity, so they react to the security champions, you know, the security team here, activities. But the reality is that the question that you want to ask is how much damage, right, can be done in hours, days, weeks, or forever, right? And this is the thing. So you might have a really high vulnerability here, and you might think, this is really bad because there's a really bad vulnerability that can do a lot of damage. But if we can detect it, and of course the other part here is how can you detect? So the variation of this is to say how fast can you detect? So in this case, in fact, let me just map that out. So if I came in here and now I did a mapping where I said, let's say, you know, in red are the ones I can detect so I'm going to put in green the ones that I'm confident I can detect very quickly, right? So these are the ones that, let's say, I can detect, super quickly. And then in red are the ones that I'm actually not able to detect, right? So you got that, and you got, let's say, this one here, right? And you got, let's say, these are the ones that I'm not able to detect easily, right? If some exploitation is happening. The interesting part of this is that, when you now start to understand this, you realize that your security efforts should actually be, you should be focusing here, right? And actually which is basically on this purple, and you should not be focusing on the blue ones, right? Because the reality is, although, and the irony here is, from a risk point of view, the ICAP service, which is the one in blue, right, might actually have less risk profile than the adaptation outcome, these other tools that I just highlighted in blue here, right? Because the third-party NCFS, right, and the adaptation outcome, if we cannot easily detect and they take weeks to mitigate, they will be way more dangerous, because the window of opportunity for the attacker, it is that greater. So now you can see that we have context, because we can now choose and we can make sure that the security activities are focused on the right things. So I would argue that, the security budget, the security teams, the security champions, the security efforts, or, should be focusing on, moving in a way, and this is again the Worldly Maps concept of movement. You kind of want to make sure that you are pushing, right, these guys to the right. So the logic, we want to move, these items to the right, because we want to change them, in 2 weeks, if not hours. And, we want to change from red to green in the kind of the detectability of this. And this is where, when you go back to in the theme of this conversation, this is where context is king, because this is where you should be able to see the security strategy when you map it like this. Cool. And that's kind of the content I want to talk to you guys. Any questions?
Hi, can I ask a question?
Sure.
So what you've done is you've mapped out 3 different things. You've mapped out the time to patch, you've mapped out the time to detect,
Yeah.
and then mapped out the what was the ease of remediation? What was the the impact, wasn't it?
No, so I mapped out the time to remediate, right?
Yep.
The hours, the time to detect, and then the security focus.
Right. So at what point do you do what you've done and mark up this, or do you map out and then blend the maps?
Yeah. So, you mean in markdown? Sorry. What do you mean?
No, you've marked up your map here.
Yeah. So, the only reason I had to draw it because I don't have that map yet on this stage. But that, give us a couple of weeks and we'll have it, right? But you're absolutely right. So what you want is you want to have multiple maps, one for each of those, and then you actually merge them together, right? And then you see the diff and you see the inconsistencies between those maps.
And how would you recommend merging those maps together?
Well, that's one of the projects we're working on right now, right? So for me, the pattern here is that you want to store the content in a graph format, right? So you need a graph, which is basically, the way I look is nodes and edges, right? So you need a graph-based environment, right? And there's some technology that I've pushed. There's already we have some code samples. Again, they're open sourced, right? That start to do some of these things. But the logic is that you want to have a graph structure that stores the graph elements in nodes and edges, right? And then basically they have properties, and then you use that, you filter that, to create the maps programmatically. So that's literally, the project that we have right now. I haven't seen a good way of doing it, but we're doing that project open source. So if anybody wants to join in, please do, right? But the solution is you put the data into code. So you have, basically data in JSON or YAML formats or in Jira. So, we've done variation of this in Jira, right? I've done a map that actually uses Jira metadata to move the things around. So you have a nodes that each of these, if you think about it, each of those in the ICAP service, right? Each of those elements becomes like if you look at, each of those elements becomes like the ICAP service, right? Has its properties, right? And then it's about creating programmatically. So you need to write code for this, right? There's no way around it, right? You need to write code that would then extract and write a query that extract the view that you want to do. And in fact, one very key concept here is that you don't have just one map, right? So you have maps within maps within maps. So the logic would be that each of these guys here will be a map in itself, right? And the irony of, for example, of this one, you can see that if I zoom in, for example, into the adaptation request, I might find that the components of the adaptation request, some of them you can patch in hours, but this is a good example of you get the lowest common denominator, right? So it doesn't matter if of the 10 components inside the adaptation request, you can fix or you can detect very quickly. If there's a couple that you can't, then that will be the metric that you have to measure.
Cool, thanks.
But that's the project that that's one of the projects that we're doing, and that's one of the things again we're open sourcing, right? Is how to visualize this and how to store this data in a graph environment. And what I like about this project is that because of all the project is open source, we can actually do this stuff for real. My biggest frustration in the past is that when I done some of these and they were quite evolved, I could never share anything I've done and I could never evolve, because there's a moment where unless you start this already open source, nobody will allow you to publish this, right? Unless it's already open, right? So for example, like I could have not created this presentation and shared this if we haven't already opened up and anonymized this version of the design, right? So, and this is kind of the game, right? So if you don't have a way to already talk to this in a public way, then it's very hard to share. So there's actually a map that I want to create that shows our open source strategy and how by opening up a lot of this information, we reduce the amount of secrets that we have, and we actually have a very effective design patterns that allow us to collaborate and even do a session like the one we're doing now. And I want to do a lot more Open Security Summit sessions around this, because I think it's, we have a good opportunity to really move the industry forward on the threat modeling, on the automation, using real world scenarios versus kind of, some of the more Mickey Mouse examples where, they're not that applicable in the real world because they don't have real world complexities.
Very, very cool.
Yeah, so please participate, collaborate, right? This is, the way I look at it is, we're trying to move the things forward, but also to find gaps, right? Like in a way, you can do now, a pen test on paper, right? You can look at this and say, why are you doing like this? What are the gaps? Like the thread model in a way is quite cool. And one of the challenges now that we have is how to create this programmatically, right? How to create, and when I the team that was doing this, that says, look, I want 10 thread models. I don't want one, because, I want thread models that, for example, look at this from all sorts of different angles. And you can only do that when you dynamically generate, designs like this. So in this case, we need to do a threat model just for what happens when this guy pops, what happens when that guy pops, what happens when the ICAP server is attacked, right? Or what's the attack surface from that side? What does the threat model look for different types of threat agents, right? And that's also very important to take into account, because if you don't do that, you end up having a massive salad, right, of what's it called, of threats. And in fact, one of the things that I'll recommend you guys taking a look at it is I did this presentation, which again is a good example of what you do when you're applying for a job, right? So actually, I did this presentation which I shared because I didn't get paid for it, right? So it was part of my research of it. But one of the cool slides that you got here, and there's some really cool stuff on here, right, on how to think about it, etc. One of the cool slides that I've mapped in here was this one that talks about the desired, the threat levels and preparedness, right, and how you should be, should be thinking about this. And the logic should be that your system should be able to neutralize the cyber vandals and the cyber crime crowd, should be able to break the economic model of the crime and the cyber surveillance, and then detect and contain the cyber espionage. And okay, cyber warfare, I probably would call it nation states. But again, it's important to map your threats, for example, to this in your graph, so that you know that what's realistic and what's not realistic, right? So you know that when you look at your architecture, realistically what can be compromised and what level of sophistication the attackers will have, and realistically which one of these will pop. Because you do need to ask the question, what happens if that is compromised? What happens if that one is compromised? What happens if some of these guys don't work the way it's supposed to work? Cool. And that's kind of it, right? That was kind of the idea, right? And this is to be one of many, and we actually want to do this now every month. So hopefully by the next month we'll do a number of other sessions on the kind of the evolution of this project, but also the threat modeling and the graphs and interconnections, and how everything kind of fits together on this and all the open source components that we've got. All right. Any final questions? All right. If not,
thank you,
you
everyone.
guys have a great night. And Fabian, you can stop the recording.